Hi, welcome everybody. As Professor Goodwin said, I teach geology here at Centralia College, and I'm very, very pleased to introduce three of my 270 students who have been working very hard this year on completing posters and projects. The first one that we are going to listen to is by Marcus Ashton. Marcus is graduating this quarter with his AS in geology. He is starting Central in the fall to continue his BS in geology. He's been sustainability and service coordinator for the SALT group at Centralia College, and I'm very excited to watch his presentation on the volcanic hazards of the Pacific Northwest.
Hello everyone, my name is Marcus Ashton. I'm a geology student here at Centralia College, and this is the volcanic hazards of the Pacific Northwest. So as we can see in figure 1, there's a 3D model of kind of what's going on underneath our feet. This oceanic crust here is going down and subducting underneath this continental crust here. And this will actually cause the oceanic crust there's water trapped in the oceanic crust, and it actually evaporates and starts to burrow its way towards the top of the continental crust and actually make these volcanoes known as the Cascade Volcanic Art. That is what we see in Washington State, and this volcano type that we see in Washington State, as well as throughout the Pacific Northwest, they are called stratovolcanoes. And they have high levels of silica content, and they make them very explosive and hazardous to humans in the surrounding area. Here in figure 2, this black line shows the subduction zone. This on the left being the oceanic crust, this on the right being the continental crust. These triangles
I think we might have lost the audio there, Marcus. Would you be willing to kind of just give us a rundown? Audio's back.
Yeah, that would be
so fine. I'm wondering if it's because I'm muted. Let's try it again and let me know if it doesn't work.
I'll be referring to it as we talk
there we go.
That come with these things. Usually a stratovolcano will actually erupt vertically, and this sends a plume of ash, and which rain down pretty much on the surrounding area and the surrounding states next to the volcano. There is what we call a pyroclastic flow. This is a result of like ash and such. It's pretty much like a hot cloud of ash and volcanic material. It also carries gases like hydrogen chloride and hydrogen sulfide, which are very dangerous to the surrounding public and the area that it goes to. There is what we call a lahar, or pretty much just a mud flow. It has a consistency of either thick water or wet concrete, so it kind of varies. But this will travel actually down river systems to the surrounding area and go miles and miles past what we think what would be a hazard area of this volcano. And so here in figure 4, this is an eyewitness photo captured of Mount St. Helens as it erupted. And Mount St. Helens is a weird one because it actually was caused by the largest landslide in history. And so this landslide cut off one side of the volcano and created a direct port of where this pent up energy could go. And it is reported that the power of this lateral blast was equal to 500 Hiroshima bombs, which is really crazy and eye-opening to the amount of energy that it carried. Like I said, this landslide that was the largest landslide in recorded history was 0.6 cubic miles or 3.3 billion cubic yards of material that came down into the surrounding area of the volcano. Pyroclastic flows followed right after, being a huge cloud of ash and such. And there is an area, what we call the Pumice Plains, next to Mount St. Helens, and it is 5 miles. It was carried 5 miles north, and these Pumice Plains were a result of the pyroclastic flows. The ash plume that was from Mount St. Helens carried ash over the United States in just 3 days and covered the whole world in 15 days. And this was a result of the ash getting into the atmosphere, and it was observed throughout the whole world in just 15 days. And these lahars, they swoop down the mountain, and the material and water bound together into a mixture. And these followed down the river systems, like the Columbia, Toutle, and the Cowlitz, being major rivers down in the southern part of Washington. They were kind of the roadway of this lahar as it traveled throughout the southern part of Washington State. Although this had a bunch of impacts on the Earth, it also had a lot of lasting impacts to the humans. 57 people died in the result of the eruption, but many more were affected just because the ash, it carried crystalline silica, which created these diseases called silicosis and COPD. And there's a lot of people who were affected by this. And this volcanic eruption also created a lot of economic impacts. Land and rivers covered with volcanic material, hatcheries being destroyed. There's reported 12 million baby salmon and around 40 million young salmon in the rivers that were killed just from this eruption. The logging industry, 4 billion board feet of lumber was damaged or destroyed in the eruption of this, and that was partially due to the fact that it erupted laterally instead of vertically. And the power actually just swept down the valley and into, you can see there's just old growth trees just floating in Spirit Lake, and this crater here is kind of a result of that, or a cause and effect type of thing of these trees floating in Spirit Lake. And there are logging operations and that were created, and about 25% of the lumber has been saved through these logging operations. And in summer months, around 600 truckload worths of lumber is saved per day, which I think is really cool. And as we close this up, I want to say that these, although Mount St. Helens erupted like 41 years ago, it still shows examples of how explosive and damaging that these volcanoes can be. And like the lateral blast, which wasn't really expected from Mount St. Helens, these pyroclastic flows going down the mountain, carrying hot debris and gases, these ash falls, blanketing everything like snow. these lahars would take over river systems and pretty much destroy everything in its path. It's still relevant to us today because Mount Rainier is the largest stratovolcano in Washington State, and there was 57 people died in the eruption of Mount St. Helens, but there's a reported 80,000 people in their homes would be at risk just from Mount Rainier's lahars. And there are major, roadways and key infrastructure that these lahars are projected to cross that would absolutely wipe out, like there would be a huge economic failure just from the destruction, just from the lahars alone. And although there's been research on the Mount Rainier lahars, there still needs to be a lot of work done just to protect the Washington State citizens that live here. I want to say thank you to Michelle Harris, as well as the Centralia College Foundation. Michelle Harris has been my advisor for 2 years and pushed me, throughout those 2 years to be the best student I could be. Centralia College Foundation, I would not be here today without their help through scholarships I got at the beginning of my college, career. From them, I couldn't thank them enough for putting on this capstone project. I love doing this project, and I hope you guys enjoy this project as much as I did. Thank you, guys.
Yay! Great job, Marcus.
Okay. So do we have questions for Marcus? We've got about, my schedule here, about 6 or 7 minutes for questions, and I'm gonna try to grab the his poster so we can share his poster too.
So I do want to say that there was in the impacts of humans, there was 12 million baby salmon who died in the hatcheries, and only 40,000, and not 40 million. I misspoke there. But there's 40,000 young salmon in the rivers that actually died because of the eruption. So I see a question in the chat saying, knowing what you do now, how are you thinking about where you want to live, like hazard zones? I love Washington State, even though there's a lot of hazards that come with, like the volcanoes and like earthquakes and such. I love this area just because there is such a diverse terrain. You could either be next to the ocean, or you could be in the desert on the eastern side of Washington. So it's so the terrain is so diverse. Do you think there's any danger that Mount Rainier will erupt laterally, or do signs suggest? So I was talking with Michelle Harris about Mount Rainier, and she kind of pointed to the fact that Mount Rainier is really, really unstable, and it will, the sides of the mountain or volcano will kind of just give way without any volcanic eruption. So I personally think there's a great chance that it could do the same thing as Mount St. Helens and erupt laterally because of the sides being so weak and how they just fall off without a volcanic eruption. So the lahar maps are saying that the lahars will travel kind of towards, it kind of cups towards the Puget Sound, and this is a figure I wanted to show in my project, but I just didn't get around to it. There wasn't enough spacing and such. But the lahar zones from Mount Rainier, they all cup towards the Puget Sound, running through like Puyallup and Tacoma, and this is a like pretty good hazard zone, and key infrastructure that would be destroying. So Carrie asked, as you study geology, what are you thinking you will focus on? I want to focus, actually, I'm gonna be honest with you, I don't really have a focused plan. I want to get my degree and kind of branch out from there. Personally, I don't want to be sitting behind a desk, and I think geology captures that greatly because you're always on the move and you're always doing surveys and stuff like that. In Central Washington University, I'll be doing land surveys, which I've never done before, but sound really interesting. So I might go down the path of land surveys, but I might also go down studying earthquakes or volcanoes and stuff. What do you look forward to at CW as you continue? I just said, I'm really looking forward to those land surveys and little projects and field trips that we will go on. Field camp. But I'm really excited for those, just so I can broaden my horizons on what I really want to do with this degree. And I think the terrain and everything around Central Washington University is so diverse. So you get kind of every little aspect of geology when you're living in Ellensburg. Did I miss any questions? Hopefully I didn't.
I don't think so. That was great, Marcus.
So thank you guys for listening in on this project, and I hope you guys enjoyed it.
Thank you so much, Marcus. Okay. All right, Michelle, do you want to introduce your next student?
Yes. So my next student is Harrison Collins. He actually has his bachelor's in science and physics already, and he has decided to pursue geology as a master's project. So he's been taking classes with us here, geology classes here, and other classes at SBSCC. And he was just accepted to the master's program at the University of Iceland, which he will be starting in next fall. So we are super excited. Really hope that he continues to send us awesome volcano pictures as he makes his way to a whole nother country with lots and lots of volcanoes. So very happy to share this project that Harrison's done in collaboration with the Department of Natural Resources in Washington State.
Okay.
Okay, hello everybody. My name is Harrison Collins, and today I have for you Mapping the Columbia River Basalt Group through Hyaluroclastic Outcrop Geochemistry. Our project is about trying a new methodology that might be able to get around a big issue in mapping geology when basalt group lavas. As well studied as these lava flows are, there are many regions throughout the Pacific Northwest and Eastern Washington where unconformities exist, where erosion has taken away all evidence of these lava flows, except for potentially the hyaloclastites. Hyaloclastites are basalt lava flows that have interacted with a body of water, cooled rapidly, fractured, and turned into a glassy debris. They're very much chemically altered, but some of the samples within hyaloclastic outcrops do not fracture. They don't fracture. These are called tacholites, and they're the thing we're most interested in. Basically, what we're trying to figure out is, can these tacholites, these glassy basalts, can they be used to determine the lava flows that created them? Because if they can, we have a way around this issue of unconformities. So let me zoom in here on my project a bit. Needs to load for a second, but basically You're probably familiar with the Columbia River basalt groups. This is a picture of the region they've inundated. There are these flood basalt eruptions that have come from fissures. They've covered much of eastern Washington. You've probably seen those black towering basalt columns throughout eastern Washington if you've ever been there. They're really beautiful. And as I said, they're very well studied. But again, we have this problem of unconformities. And so we're going to see if we can get around that problem using these hyaloclastics. So what we did is we went to these locations throughout eastern Washington. This is a map I produced of the area that we've covered. And in each of these locations, we just took samples. We took a look at an outcrop like this one right here. And after using a rock pick, rock hammer, and just kind of hacking away at this thing, we would end up with samples that look like this. So something I want you to take a look at here is notice how much of this rock is very tan, brown, even yellow. That's not what basalt looks like. This is completely chemically altered. But some of the samples here, like this part right here, and especially this sample right here, are shiny and black. This is what we're looking for. These are glassy basalts that come from an outcrop like this. So we sorted these, we cleaned up these samples, and then we sent them to Hamilton Analytical Laboratory, where they did traditional XRF spectroscopy, as is done for normal lava flows. And what we found is given by these graphs right here. So stepping through this a little bit here, each of these colored lava flows represent, or colored samples here, these are not the samples we collected, but instead a database of samples that have been curated by my project advisor and also produced by Hammond 2013. So each of these circles and the ovals around them is a group, is kind of grouping them together. Those are well-known, well-established lava flow chemistries. My samples are the ones that are numbered, like this 12, this 9, 9A, etc. These are the tacolite samples. So what we find is we find very strong agreement with stratigraphically expected chemistries of our tacholites and what we see in the actual geochemistry. Standard techniques involve comparison of titanium dioxide and magnesium oxide, and some people also opt to include a second graph that uses P2O5. This is kind of the standard technique. And we see excellent agreement between these two samples. Between these two graphs. Almost all of the samples, barring number 3, have the same correlation groups in both of these graphs, and they're pretty closely related to the lava flows that they're being paired with in both cases. So what this tells me is that this method is capable of producing resolvable geochemistries that are consistent with stratigraphic expectations when they are there, and when there aren't any, in the case of this sample right here, we have a methodology that we know works for these guys, so we can use the chemistry to motivate the stratigraphy instead of the stratigraphy being validated by the chemistry or validating the chemistry. We have a technique here that works. We have a technique that doesn't require stratigraphic background to determine what created these glassy basalts. So kind of getting to the conclusion here, like I said, this technique works. This technique bypasses the problem of not being able to access the lava flows, the lava flows as they normally are. We just need to have hyaloclastic outcrops in locations of unconformities. And if we do, we can use these to determine the chemistry of the lava flows that created them. This is going to be a pretty big deal for mapping geology because we have a way around a huge problem. So that's basically my project. I'm really pleased with what we got out of this. I have some acknowledgements I'd like to share. I owe the Centralia College Foundation a lot of thanks for funding this project. I owe Rick Conway and of Hamilton Analytical Laboratory a lot of thanks for expediting the process of the sample analysis to help me get this done. I owe my project advisor, of course, for bringing me on board with this. I really appreciate the experience he gave me. And I owe Professor Harris many, many thanks for being really patient. This project was a demanding one, but I'm proud of what's happened. She has been patient with me as I've worked through this. So here are my references, and thank you very much for your time. I really appreciate it.
Okay.
Sorry that was blurry, everybody, but thank you for your time.
Yeah. I asked it to optimize for video. Maybe that didn't work. So let me share his poster so you can talk through it a little bit better as well. Let's see.
Well, it's still got the make signs insignia, so you know it's authentic.
Yeah, well, I'll get rid of that in just a minute, but we have to give them credit too.
Yeah, I guess they should be in the acknowledgements, maybe.
Go ahead and start developing your questions if you haven't already while I figure out why this thing is not.
Yeah. So I'm going to answer a question here by Dr. Kelsey. So sample number 3 is kind of interesting because there was an observed trend with one of the graphs versus the other graph, that the P2O5 graph, the second one, we believe the process of forming tacholites is a process that diminishes the amount of P2O5 that can be found in the magma, because when the basalt interacts with the water, it has the potential to change chemically quite a bit. And certain elements, certain chemicals are much more stable. Like magnesium oxide isn't really phased that much by this based on our results, but P2O5 does seem to be somewhat significantly altered. And so sample 3 was kind of pushed over the edge from being correlated with the purple samples, which represent the Ortley lava flow, and it was pushed into McCoy, despite the fact that the stratigraphy suggests that Ortley is indeed the right projection for number 3 based on where it is in eastern Washington. Other than that, there was a little bit of change with other ones, but it wasn't enough to be significant for correlation. It was only number 3. Hopefully that helps. Let's see what else here. Oh, shoot, a couple more questions. Okay. Do you think this technique would be useful in characterizing the source of sediments? Well, see, sediments are interesting. Let's see here. So do you think this technique would be useful in characterizing the source? Well, I think that depends on where the sediments are coming from. This CRBG technique is very, very well tuned towards those lava flows specifically. And part of my findings were actually based off of a machine learning algorithm that was used in the sample analysis. So I think if we were to try to use this, use this technique on general sediments, we'd have to do a lot of work with the sediments themselves and get around the fact that sedimentary deposits tend to be made of a whole bunch of stuff instead of being consistently from one magma chamber body. Hopefully that makes sense. Let's see, try getting better dimension resolution with a multi-dimensional analysis with a PCOA. I'm actually not familiar with a PCOA, unfortunately. There were what I tried doing is comparing the chemistries of multiple beyond just TiO2 and MgO. I also did other ones, but there wasn't enough room in this poster to show all 6 graphs I produced. I compared TiO2 to MgO, to P2O5, to calcium oxide, zircon, barium, and chromium, as suggested by some of the top researchers who use that technique when they're doing these correlations. But I wasn't able to show all that. That's just one of many ways to use more than. Oh, I see. Okay. Well, in my findings, I haven't really seen people use 3-dimensional analysis like this. People have been able to do it with 2-dimensional analysis by just throwing a whole bunch of graphs at you and just kind of digging through them. And but that's a really interesting idea of comparing 3 different chemistries. I'll have to look into that. So thank you for that. Yeah. Yeah, I know. It's a lot to take in. Geology is kind of its own little corner of science, so you kind of never know what you're going to get sometimes, I feel like, or at least that's been the case in my experience, but hopefully that was somewhat interesting for you. Let's see here. Are there any other questions I missed here? That appears to be all of them so far. Yeah, so Marcus, hypothetically speaking, this should be a technique that should work on all different types of lava flows, provided that you're tuned into those lava flows. The reason we're doing it on the Columbia River Basalt Group first is kind of first off, logistically, you know, it's a 3-hour drive, but it's not like going to Iceland or going to India or going to wherever, or Greenland, where there are a bunch of other flood basalts. This one's in Washington, and it also happens to be extremely well understood in terms of its layers and also its chemistry. So I felt that the Columbia River Basalt Group was a perfect test case to start this idea, because we have such a robust understanding of the lava flows where they're exposed that results should have been immediately obvious if we understood where these samples were spatially, and the methodology we used to prepare them was adequate. And thankfully, both of those things appeared to be the case. So with a little bit of doing, a little bit of kind of attuning to the lava flows you're working with, this technique should translate to any lava flow, as far as I know. Thanks, Marcus. All right, well, thank you very much, everybody. Unfortunately, I'm probably gonna have to log out because I have to present a very similar presentation for South Puget Sound, but thank you everybody for your time and really appreciate your questions.
Great job, Harrison.
All right, everybody, thank you.
Thank you, Harrison. Good to meet you.
Good to meet you.
All right, so next, as Professor Goodwin's pulling up the poster, we have Isaac Pope, who is going to present his work that he's been doing on the Mima Mounds, something that us as geologists and biologists are still unsure of their origin. Isaac is actually a running START student. He's working on completing his AS in geology. He's also a geology tutor and serves on many campus committees. He has produced about 30 publications in peer-reviewed journals and scientific conferences through GSA and AEG, which are two geologic groups. The poster that he's sharing today was presented at the GSA Cordilleran meeting this year. And he is also a book review editor and peer review editor for GSA and AEG, which is Geologic Society of America and Association of Engineer and Environmental Geosciences. So very happy to welcome Marcus. Sorry, I was looking at you, Marcus. Isaac.
Thank you, Professor Harris, and thank you all for being here today. It is my extreme pleasure to talk with you today about perhaps one of the most baffling mysteries of Washington geology. So this project began with Pat Pringle and Michelle Harris last spring already, and we found some incredibly exciting results, and this poster goes into some of those aspects of it. So the Mima Mounds of the Puget Lowland are dome-like ellipsoids of sediment, which we call a diamicton, where there's a variety of different gravel sizes that then go down to sand to clay size. And with these mounds, we find on proglacial terraces all throughout the southern parts of the Puget Lowland. And these mounds, which can be up to 6 feet high and over 10 feet in diameter, we can find these in the thousands along some of these prairies in Washington state. And for well over 100 years, these mounds have been a major mystery to geologists as they've been trying to grapple with the origin of these mounds. And that mystery has only gotten larger as we've gone to other areas and found that there are very similar mounds, which we like to call Mima-like mounds, and we can find them just about every continent. And of course, even just all across the United States. So there's the real mystery of finding out the origin of the Mima mounds here in the Puget Lowland and how they relate to other mounds throughout the world. So as you see in the lower left figure, you can see an aerial photograph of the Mima Prairie. And right next to that aerial photograph is Lidar Image. And Lidar is where they're able to essentially take pictures of Earth's surface through, it's kind of like radar in a sense, But throughout this process, they're able to visually remove like the vegetation and trees. That way we get a very close approximation of what the actual landscape is like. And what we can see from these geologic investigations, that the Mia mounds are not perfectly round. And that's been one idea that's really helped develop a certain, or been a key part of certain developing models, is the shape of the Mia mounds. So when we look at the Mia mounds, we find that they often elongated, and you can see circled. I like to call these mound trains because they're elongated to such a point that they even connect to each other by low bridges in between mounds. So when we look at the origins of the mounds, we find a variety of hypotheses that are based on these different characteristics. And some of the big ones that we'll be looking at today are the rodent hypothesis, which a lot of biologists like to look at, in that they think that rodents like gophers helped develop these mounds, kind of like molehills, but eventually these developed over quite a long time to develop these mounds. And another idea has been that the wind has carried the sediment into this area, and it got accumulated around vegetation. But a competing hypothesis, at least for the origin of the sediment itself, was pioneered by our very own Pat Pringle and some of his colleagues, looking at how a glacial meltwater flood from south of Seattle was released and would have covered many of these terraces and deposited this dimicton, which looks very much like a debris flow deposit. So you can see that in the lower right figure, a map of what the Tanrax flood coming from glacial Lake Carbon would have done. So when we look at when we look at the Mia mounds, we find that oftentimes these mounds are not perfectly round, as we've mentioned before. Ken Tabbitt at Evergreen University used Lidar and GIS processes to figure out that most of the time, these mounds are elongated parallel to the downslope gradient of the host terraces. That's saying that even though the terraces are pretty much flat, there's a very low gradient, and those mounds are almost always going down in that direction. And when we look at when you actually go out into the field, we find many interesting cases of this in a variety of different prairies, and they can vary greatly. Like if we go to West Rocky Prairie, we will find that they're pretty much round, except for one interesting case where in one of our geologic investigations, as you can see in the Lidar image, there are, you can see they look like channels. They're lenticular low areas that go across these prairies. And inside those sinuous structures, we find very small mounds in comparison to all the others. So instead of being 6 feet high like we find with the mounds around it, inside these miniature channels are low mounds, perhaps 3 feet high, and they're highly elongated. So when we look at all the field data on these different aspects, we find that not only do mounds in general are they elongated down slope, but even in areas that look very similar to channels, they can be highly elongated. So this then raises the question, why are they elongated? And we look at all the major hypotheses, we find that most of them drastically fail in explaining this elongation. Like even if we look at the rodent hypothesis, the gradient is so low that the rodents aren't going to, through their processes, intrinsically cause the mounds to be elongated. And also when we look at the paleo wind patterns, we find that most of the time these the direction of elongation is going in a different direction than the wind currents. And another problem, especially when we look at hypotheses based on wind, is that oftentimes you can find large cobbles and boulders in the intermounds or the low areas between mounds. And there's very interesting patterns we can see, and I talk about that in a previous GSA presentation. But those cobbles and boulders are of the same type or lithology as the other the other class of rocks inside the mounds. So this is very suggestive of not only the diamicton having been deposited by the Tanwax flood, as previous studies have shown based on the lithology and provenance, but this shows that the elongation of the mounds is likely closely linked to the Tanwax flood itself. Not only was the diamicton deposited at that time, but the mounds' origins, not just the sediment, but the origin of the mounds themselves, must be closely linked to this debris flow associated with the Tanwax flood. And I hope through further investigation to be able to flesh out that hypothesis of exactly how intertwined are those two events with each other. Thank you.
Great job, Isaac.
Thank you.
Okay, questions for Isaac. And Isaac, if you would like me to pull back up your slideshow while questions are being asked, just let me know and I'll be happy to share that again.
Okay, thank you. Now here's a pretty good question in the chat. Is the elongation found in all mound areas worldwide? Now that's an excellent question, and I think that's something that should really be investigated more, just because some of the major ideas for the origin of the Mia mounds is actually based on the mounds being roughly symmetrical. That's one of the main assumptions underlying the rodent hypothesis, for example. And when we look at elongation in different prairies, we find that they can vary quite widely. Like if we go to the Columbia River Gorge on the Oregon-Washington border, we find that some of the mounds are highly elongated indeed, depending on if they're on terraces associated with the Missoula floods, or if they're on other surfaces. Also, if we go to places like Oklahoma, they can have some elongation, but there's been a lot of research there that indicates that the elongation there likely is due to wind deposition of those mounds. For example, it's mostly just silt there, and there aren't all the big rocks inside those mounds in Oklahoma as we find at Mima Prairie. So there's still a lot of debate on how even the mounds here in the Puget Lowland, if they're even genetically linked in some origin sense to the ones at other areas. And I guess I also mentioned in terms of that question on how the Mia mounds all relate to each other, just this month, I had an article come out in GSA Today, which is one of the flagship journals of GSA, that talks about how there's a lot of disciplinary bias that goes into studies on the Mia mounds, and how sometimes the ideas for how the Mia mounds developed can differ based on the area from which a researcher comes from. So I think there's a lot that can be said about, there does need to be more research looking at how these mounds areas actually relate to each other. Yes, thank you, Professor Pringle. Yes, so he's reminding me that I kind of skipped over some of the research we had done last spring, and this was part of a project that Pat Pringle has done a lot of work on, tracking the Tanwax flood. And one of the ways that they've been able to do that is look at the types of rocks within those deposits. Oftentimes you can look at the types of rocks within a deposit and you can get an idea of what area it came from. For example, if you find a lot of granites inside a deposit, then all you have to do is look at Washington State Geology and you can say, well, granites only come from these certain areas. And in general, if you find a lot of plutonic or metamorphic rocks, that's indication that those rocks came from up north, further up in the Puget Lowland, likely being brought down by glaciers. So what Pat Pringle and his colleagues did was they looked at the Tanwax flood deposits and they noticed that there was a very high concentration of andesite rocks due to glacial-like carbon being very close to some ancient mountaineer andesite volcanics. So in some cases, it can be up to 80% of the rocks within Tanwax flood deposits are andesite. So all you have to do is look at the rocks within certain deposits of a certain age, and you can get an idea of if those deposits are correlative to the Tanwax flood. And that's what we did last spring at Mima Prairie and several other prairies. At Mima Prairie, up to 40% of the rocks there are andesites. And that makes sense because if you look at Tamarack's flood, once it gets over to Muna Prairie, it's going to be mixing with other older glacial deposits. So you're going to have a lot of mixing between glacial deposits and Tamarack's flood deposits. But in some areas, there can be up to 80% of the rocks are andesites. So it's a very interesting correlation that definitely hints at the great possibility that the Dimicton is deposited by the Tamarack's flood. So my interest in geology, I guess, has really just been with a fascination of, our environment around us. I've always been interested in understanding all the interlocking parts of the world. Just step outside your door and just look around, and you'll see that there's so many interesting facets of nature, just begging, begging for the curious to investigate it. So I think I was about 9 when I finally got to the point where I would read all kinds of rock guidebooks, but eventually I got tired of reading about, the identity of rocks you might only find every once in a while in the Congo. I wanted to find out how to just go outside and identify any rock that I encountered. So that's where I really got into my journey of understanding first rocks and then landscapes. So incidentally, now a lot of my work is in sedimentology and geomorphology, looking at how landscapes change and how they can be recorded through deposition. And a lot of my work also goes into how that can happen in volcanic landscapes like Mount St Helens and Mount Adams.
All right, you have time for probably one more question. There were a couple in the chat that Dr. Norton asked specifically about, is there experimental evidence that like flow tanks that provide mound-like formations, or could mounds that were originally hemispherical be modified after mound formation, are kind of his two big questions.
Okay, so to deal with the first one, mostly if there's been any sort of experimental work, it's mostly been done through computer simulations, and there's some work that's been done by advocates of the Rodent Hypothesis that tries to work out how you could have mounds forming within a certain time frame by bioturbation. The only other experiments I'm aware of are essentially those by Andrew Berg, who noticed that if you put a lot of fine-grained sediment on, for example, like plywood, and then you start hitting it with a hammer, it'll actually clump up into these mound-like formations. So Berg believed that earthquakes would be the reason for the formation of the Muna mounds. Other than that, the study of the Muna mounds has been very much a forensic study instead of experimental. So that might be one thing that we're definitely seeing more in Muna mound research, is bring on the experimental and computer simulation type of research. Oh yes, so the time period of the Tamarack's flood, maybe Professor Pringle can chime in a little bit, because I think he's done a little bit more work on that. In my poster, I say 16,500 years old, near the very end of the last glacial period. But I think Pat Pringle has done work that revises that number very slightly.
Pat can put his answer in the chat if he doesn't want to speak up here, so that inquiring minds want to know now, Pat, what you have been up to as well. Okay, so we're going to, there we go. New dating of maximum. Go ahead, Isaac, you can read as well as I.
All right. Yeah, thank you. Yeah, thank you, Professor Pringle. Yeah, he says that new dating of the maximum of the Puget Lobe Glacier was 16,000 years ago when it reached Rochester. So the flood was likely right after that. Okay, so just under 16,000 years ago. Yeah, thank you, Professor Pringle. It's hard to keep up with you with all the work you do.
Thank you all.